right, today we're going to take a look at section 2.2, where we're going to measure change instead of being over an interval, because that's what we did in 2.1. We're going to measure how something is changing at one specific point in time. All right, not over an interval, but at one specific point in time. This is actually called instantaneous rate of change. And we'll abbreviate it as IROC. Last time it was AROC, and this time it's IROC. There's a couple other phrases, or another phrase at least, there are more than this, we'll do later, but that we will see used in sort of in lieu of instantaneous rate of change. Sometimes you'll see the phrase slope of a curve at a point. So normally we talk about the slope of a line, right? But when you look at like a hill, like in real life if you're driving, there's a slope on that hill whether it's a flat piece of the road or not, right? There's an incline and there's somehow a steepness to it that you could measure, and that's what this is measuring, the steepness of the curve, just like the steepness would be of the hill at a specific point in time. Last time when we looked over an interval, we used this phrase that said increased or decreased because we were looking at a set time that had already occurred. It was past tense. But when we're talking about looking at a specific point in time, it's right now, it's happening. That's present tense. So we have to say increasing or decreasing. It's not a past tense, it's a present tense verb. Local linearity is the idea that if we looked closely enough at any point on a smooth curve, right? If we like zoom in and zoom in and zoom in on your calculator, everything starts to look like lines. And you've probably experienced that before, where you looked at something and you're like, I see a line, and somebody's like, I see a quadratic, and you're like, how do you see a quadratic? Clearly it's a line. And then when you zoom out, you're like, oh look, there's that U shape. I didn't see it because I was zoomed in too far. So this idea of this zooming in and this local linearity, a line that sort of looks like it's there but it really isn't, is actually called a tangent line. The tangent line at that point. Note, tangent lines do not cut through curves except at an inflection point or if you have a line already. In which case it becomes the line you already have already, so it intersects it everywhere. So once you have it written down, I'm actually going to go backwards for a second. I'm going to draw you a couple pictures that you might remember from geometry. That phrase tangent line might be something that you're like, I feel like I've heard that before, but I don't remember exactly what it meant, or maybe I do remember what it meant, but it wasn't related to calculus, maybe especially if you haven't had calculus. And what it was related to, I'll flip back to this one in just a second, so just pause for a second if you're still writing. What it was related to was the idea of circles. So you had things called tangent lines and you had things called secant lines. So a secant line did this, it cut through the curve, right? Cut through 2 points on the curve. But a tangent line actually just barely touched the curve, right? Circles specifically in geometry. But it's the same idea even when we're working with our curves that are not circles. They just touch them as well. So tangent lines will do this. They will sort of bounce off the curve. I had a student once tell me they kissed the curve. Just barely touch, okay? Barely touching the curve. There are exceptions, and an inflection point is one of those, and I'll show you a picture of that on our graph that's coming up, so you can see how it looks different when it's an inflection point. Okay, can I switch to the next slide? Is everyone good? Still see people writing, so nobody wants to talk, but okay. Here's my graph. I'm actually going to draw some tangent lines so you have an idea of what's going on here, but this just says at each point decide if the instantaneous rate of change is positive, negative, or zero, and it says by drawing tangent lines. So we're going to make our decision by drawing tangent lines. So when I draw a tangent line and you draw a tangent line, they should look pretty close, but they may not be precisely exactly accurate because we're approximating them to some degree. Does that make sense? Get out something that's a straight edge. All right, something that's a straight edge. I have the tools on my screen so that I can make straight lines. You probably have your pencil. It doesn't make straight lines all that well, right? So grab your ID, grab the edge of your calculator, grab an edge of a sheet of paper, something that's kind of firm enough that will provide some backing. And what you're going to literally do is you're going to line your paper or whatever you have. I'm going to use paper so you can see it. So that it hits that curve like we talked about, but it doesn't cut through it. I know what I can use. So if this were my line and I'm cutting through it, I'm going to hit it like right here. Okay? So that's what we're going to do for A. I'll draw mine on a screen. Something kind of like that. It's not perfect, but it's have the right idea. So if I've drawn that, and you've drawn that, our question is to decide if the slope of that I just created of that line, right, that I created a line at the point A, is that slope positive, is it negative, or is it 0? What's the slope of that line? It's positive. It's a positive slope. Agree? Yeah, it's a positive slope. See, it's increasing. The line's increasing, right? It's going up, so that's a positive slope. Now, B is actually an inflection point. Can you guys see that okay? We've talked about cubics before, and it's kind of got that visible piece that looks like the cubic in the middle anyway. There's an inflection point in between there. So what do? Well, it's somehow still got to sort of hug the line. So I know this said over here at inflection points it cuts through, but that doesn't mean you can cut through willy-nilly any way you wish. That is not a tangent line. Okay, I don't have flexibility like that. I still have to draw a line that if I were to zoom in would be almost indistinguishable from the curve itself. It looks like it's the same thing. So the line ends up getting drawn something kind of like that. Now it did cut through, and the reason you know for sure is because we're below the curve over here nearby C, and we're above the curve way up here at the top, right? So it definitely cut through the curve, but it does it in a very specific way. So again, our images may not look perfectly matched, but they should look pretty close. What about the slope at B? Positive, negative, or 0? Negative. All right, it's going downhill, so negative slope. What do you think the tangent line might look like at C? Huh? Say it really loud, Sarah. Or Paul, who said that?
Horizontal.
Horizontal. Yeah, it will look horizontal. So here, let me actually justify why that's the case, because it sort of seems like, I mean, okay, fine. She said horizontal, so it must be horizontal. But there's a reason for it. If I were doing tangent lines before here, they would all be sort of getting closer like this. Do you see that? The tangent lines themselves, my ruler would be shifting in that way. And on the other side, this opposite would be happening, right? The tangent lines would look like that, and they would look like that, and they'd look like that. And eventually, where do they both sort of converge? To a horizontal. They do. So I end up with a horizontal tangent line at C. What is the slope of that line? Yep, that slope's 0. So now here's the fun thing that we just found out. Anytime we have a peak or a valley like that, we get horizontal tangent lines of 0. Happens all the time. Okay? It will. How about at D? Well, it should look, mine's not going to be very good, so I'm going to shift it just a second. The benefits of my screen, right? It looks something like that. Positive, negative, or 0? Yeah, it's positive. That slope is positive. What will your line look like at E?
Horizontal.
Horizontal again, it's peak, right? Just like at C. So its slope is 0. Okay, any questions on those? All right. Now we're going to find one where we actually calculate the slope from a graph. So our directions say use a carefully drawn tangent line So we're going to be careful, which we should be careful anyway, but specifically here, be careful because we're going to use this tangent line to estimate the slope of the curve at the point. And it tells you that each mark represents 1 unit. So first things first, draw a tangent line. And I would make sure your tangent line extends sort of far out in each direction because it would be really nice if it hit some axes here. It's easier to calculate where you are sometimes if you're actually hitting the X or the Y axis. So like when you draw this, sorry, I have the line tool. Notice I hit the X axis, did it on purpose. It's easier to calculate that point to me. So there's my carefully-ish drawn tangent line. And I'm calculating slope, but y'all know how to calculate slope. That's algebra, right? Yeah, that's algebra. And it's also what we did in the last section when we calculated average rate of change. So slope, not slop, let's try that again. Slope is y2 minus y1 over x2 minus x1. That's what it is. And I need 2 points in order to do that. So if we take this point we're at right here, the dot that's actually on my curve, I think realistically that looks kind of like the value 3.5 and 4. Does that seem reasonable? Did yours look like it about 3.5 on the x value and 4 on the y value? Yeah? Okay, good. And then you can take any other point on the line that you want. It has to be a point on the line. Can't be a point on the curve, right? I can't choose this point over here. That's not anywhere near my line. It has to be a point on the line. But this is why I picked a line that actually crossed the x-axis, because it's easier to see that particular point. And not only that, but one of the ordered pairs is 0. I like ordered pairs where I have numbers of zeros. They make calculations nice. But the x value is at maybe like 5.7. I don't know, approximately. Okay, does that make sense? If you didn't want to pick that point, you could pick anything else you'd like, right? You could pick, say maybe you thought, hey, look, this one looks really good. I'm going to use that point. Okay, use that point. And so what you'll do is you will draw your dotted line sort of down here, and you'd estimate with that particular point instead. It doesn't matter what point you pick. Your estimations will be very close in whichever option you pick. So we're going to calculate slope. So we'll call this my x1, y1, and we'll call this x2, y2. So y2 is 0, y1 is 4, x2 is 5.7, and x1 is 3.5. Does that look good? Seem reasonable? Fabulous. So I have negative 4 on top. I have 2.2 on bottom. If you grab your calculator and let it do the division for you, what do you get? These are approximations we're calculating, by the way, so what do you get for your slope?
Negative 1.818.
And with 3 decimals, that's exactly what I have as well. Okay, so we're going to use 3 decimals when, sometimes they stop before 3 decimals, I get that, but we'll use up to 3 decimals for our solution. No fewer unless we can't have this or aren't anymore, but this is what we'd have. Now, let's say that I did this problem, and Sarah did this problem, and Jacob did this problem, and Mark did this problem, and Ariel did this problem, and we all did the problem, right? We may not have the same answer, but they better be pretty close, right? So if you got an answer that was like negative 1.6, you're probably in the ballpark. If you got an answer that was negative 2.2, you might even be in the ballpark, right? But if you told me it was negative 67, you're probably not okay. There's a problem. Okay, so there are definitely some flexibility because we're drawing these by hand, but we don't have just any and every answer it's not that flexible, right? It does have a little bit of constraint. All right, one more formula in this section, one brand new formula, I should say, in this section. And that formula is called the percentage rate of change at a point. All right. So percentage rate of change at a point. I didn't get my notes rewritten after I changed something on them at one point, I guess. Percentage rate of change at a point. We had percent change at a point. So just to recall first, we're going to recall percent change. Percent change was f of b minus f of a over f of a times 100, right? Y'all remember that? Section 2.1. That's percent change. So what changes when we do percentage, I'm sorry, that's not what I meant. Rate of change. What changes? Well, it's based on the fact that this is not happening over an interval. There is no interval here for a percentage rate of change. There's a specific point in time that we're calculating for. Okay? So I want to take a step back for a second because I didn't actually write this notation down and I need it now and I should have. Instantaneous rate of change for a function f, let me write it that way. So for a function f, the instantaneous rate of change is called f prime. Okay, f prime. The instantaneous rate of change for a function f is called f prime. So when we're calculating the percentage change over here, it's f prime at that value, whatever that value a is, divided by f of a times 100. So the denominator stays the same, the times 100 stays the same. The numerator is not over an interval anymore. Instead, it's at a specific point in time. Okay? That's the instantaneous rate of change. The instantaneous rate of change in that time divided by the value, the function value at that time. So we're going to calculate it based on a particular graph that we have next. So here's our graph. This figure shows the total number of cellular phone subscribers in the United States from 2000 to 2008. A is much like the last two questions we've done. Draw a tangent line and then estimate the slope just like we did in the last problem. So you're going to draw yourself a tangent line. It's going to look something like that. Okay? And you need an ordered pair XY for two of the points. One of the points at P, one of the points probably should be the P value because they put it on there, but it doesn't have to be. If it's absolutely atrocious, you wouldn't necessarily have to use it. But to me, it looks like it's at about 5 and 62, the way mine's drawn, give or take. And then again, I really like the intercepts where it crosses the x-axis is very friendly here. So it's crossing the x-axis at about maybe 0.8. And notice, what is the y value at the x-axis? Because it's actually not 0 this time. What is it? It's 45. So just because it's an axis doesn't necessarily mean it's 0. You have to be careful about how it's being drawn. So these are my ordered pairs that I'm going to use to calculate slope. So we've got our change in y over the change in x. Does it give us a function name for this? Yeah, they call it graph P right here. So this graph is called P. This is P of x. Okay, so over here I am finding the instantaneous rate of change, which is actually P prime. In this case, it's a 5 because that's my x value where the point is located. All right, good enough, I guess. All right, I need to subtract the y values. I'll just use the earlier and the later values, so I'll make this one x2 and y2, and this one will be x1 and y1. All right, so y value number 2 is 62. Y value number 1 is 45. Y value number 2 is 5. And y value number 1 is I'm sorry, x value number 1 is 5, and x value number 2 is 5, x value number 1 is 0.8. Can't speak. All right, so 62 minus 45 for 17 over 4.2. And we're getting it to be approximately 4.049. Again, it's an approximation. Yours might look a little bit different than mine. You might have looked at that and said, hey, I didn't think it crossed at 62. It looked more like 63. Okay, that's fine. No problem. This is approximately the slope of this line. Now, we actually haven't done part B yet at all. Part B actually asks us to write an interpretation for what we found. So as we're moving into there, let's just actually think about what these quantities represent. What are the 62 and the 65 in this context? What are they? 62 what?
Thousands of cellular phone subscribers.
Right, it's the number of subscribers. It's, in fact, you're exactly right. I'll highlight it. It's the 100,000 subscribers, right? And what are my 5 and my 0.8? The years since 2000. So if I'm thinking about maybe like units for what's going on here, this 17 is in the 100,000. I can't get my D in there. It's going to blend into my white. 100,000, there we go. Subscribers, and then the denominator, I didn't write subscribers because I'm out of space, but then the denominator is in years. And it's years since 2000, I recognize that, but we're subtracting them off, so it's the change in years that we've actually found, right? How many years have passed between the two times? So over here, when it asks you to find the unit of measure, that's what you're actually doing. You're just finding that this is 100,000, because that's what the numerator is, 100,000 subscribers. And then it's per, like the word per, the denominator, and that's per year. It's 100,000 prescribers per year. So there's two questions here. This is the first question, the units. The second question says a sentence of interpretation. So what we actually found is the following, or something like this. The number of cell phone subscribers, that's what was changing, right? We could actually put it at the beginning. In 2005, we'll put that at the beginning. I usually do my when first. I don't know why I didn't here, but I should have. When? In 2005, because it was, right, that was my interest level where it said P on my actual graph. In 2005, the number of cell phone subscribers was, there's the past tense, it was, but it was doing it instantaneously. So it was increasing, present tense, right, happening right then, was increasing by 4.049 100,000. You can write subscribers if you want. Again, we've already written it once, so I'm going to leave it off this time. 100,000 per year. The sentence of interpretation looks just like it did in the last unit. It's not different at all. Okay? It's just that now we're talking about it happening at one point in time instead of over an interval of time. We don't say from this year to this year. We say in this year or at this time. Right? C. C wants us to find and calculate and interpret, if I could read, the percentage rate of change at a point. So again, the percentage change, it's with the letter P. It would be P prime of X over P of X times 100. Okay, so, and it's not X because ours is in the year 5. Sorry. Right, it was at the time 2005. So P prime of 5 is what I found on part A. That was the 4.049. divided by the p-value at 5. That's the 62 that I originally found. It's the y value then. 62. And then multiply by 100. And I found that to be 6 point, percentages will use 1 decimal, so 6.5%. If you use 2 or 3, it's fine, but usually one decimal is sufficient for a percentage. 6.5%. And the cool thing is, just like when we did percent change back in the last lesson, and we did change and we did average rate of change, the sentences all look alike. All right? They don't change at all, the structure. We say in 2005, the number of cell phone subscribers it is in the past, it was happening, but it was still increasing. And why is it increasing? Because it's positive. You see in the graph as well, but it was increasing by 6.5, and it's interesting, I need to go back and add this because I didn't write it down before, but it's 6.5% per year. And you might be thinking, well, when we do percent before, just percent? And it was. The reason it's percent per year now is because this one right here was 100,000 per year. Do y'all remember that? Back on the previous slide, it was 100,000 per year. And this one is in 100,000. So what do you see happen? Yeah, the 100,000 cancels, but the per year part's still there from the numerator because it's an instantaneous rate of change instead of it just being an average rate of change. When we did it as an average rate of change, when we did it as a rate of change back in the last section, the units didn't have that. They didn't have a per year because it was over a time frame. This is at a specific point in time. So I end up with still having per year. Any questions on that? Okay, so here's what we're going to do. This assignment will be due next time, right? I'm going to start 2.3, but it won't be due. We'll just get started a little bit. That way we'll finish the 2.3 and get on into the next section after that next time. So the only assignment that is due when you walk back in the door on Thursday is 2.2. Okay? Sound good?
Are you going to post this stuff on Canvas, these slides?
I always post the video on Canvas. So like you'll hear me, it's exactly like you're hearing me talking right now. Okay? So you'll hear, that's what you'll see on Canvas. Okay? So Malo has to go, but we're going to do the next section a little bit before we all leave. Okay? So hold tight.